Alright, so for our final physics project, we did the physics of celestial bodies, and me and Jack worked on this. So first thing we need to go over is the gravitational forces, or the gravitational force equation, because that is the basis of our project. So the force of gravity is determined by the mass of two objects and the radius between them. Gravity is one of the weaker forces of the four fundamental forces, but is still strong enough to keep planets in orbit around each other. So we have a force body diagram showing how the force of gravity interacts from two different objects. So in the programs, we did not include the gravitational constant g in the calculations, as it would make the numbers too small for the computer to represent on the screen. And to the right here, you can see the equation for the force. Next, we look at the object code, which basically is making the objects that are seen in the simulation and just setting all the parameters for the velocities, the directions that they're going, the accelerations, etc. Next, we have our first problem. So a ball is launched vertically from the surface of the Earth at half the escape velocity. So we want to find out how high the ball will go. So this is a solution, a theoretical solution. So we use the escape velocity, root 2g r being the radius of Earth. And for an object to escape from Earth, we're using energy, so 1 half mv squared minus g mm over r equals 0, because the final energy would be 0 for it to escape Earth. So the initial velocity would be root 2g r over 2. The initial kinetic energy would be g mm over 4r, and the initial potential energy would be negative g mm over r. The negative because it is the opposite of kinetic energy, so the total energy would be negative 3/4 g mm over r. So when the ball reaches the height that we're trying to find, the velocity would be 0, the kinetic energy final would be 0, and the potential energy final would equal negative g mm over r plus h. So using the conservation of energy, we set the two total energies equals to each other, and we get negative 3/4 g mm over r equals negative g mm over r plus h. So then we solve for h, and we get r over 3, and then we substitute r, which is the radius of the Earth, I found online as 6.371 times 10 to the 6 meters, and we get the final height as 2.12 times 10 to the 6 meters. So now we look at the code, and we can see from this code, all the codes are structured basically the same, having the objects defined first by O1 and O2, defining the masses, the initial velocities, and everything like that. And then we also have the problem or the initial parameters being defined to make sure that everything runs smoothly, and the calculations, and then the making sure the actual code can stop by checking the collision. So once a collision happens, the code will be able to know that it's done. So next we have the code solution. So as you can see from the code output, for the farthest distance with half escape velocity, we got about 2.05 times 10 to the 6, which was almost the same. So the reason for this variation was because the time step for each loop is equal to 1, which explains why there's a variation from theoretical and experimental. So then we graphed the distance in x direction versus time, and you can see that when the slope of the parabola is at 0, that would be the maximum height of the ball, which would be our value of 2.05 times 10 to the 6. Next we have our second problem, which is a pretty common problem for two objects for 2D orbital motion. So Phobos orbits Mars with an average distance of about 9,380 kilometers from the center of the planet and a rotational period of about 7 hours and 39 minutes. So uses information to estimate the mass of Mars. So for a theoretical calculation, we used the Kepler's third law. So the distance cubed over period squared equals the gravitational force. So we plugged in all the numbers, and we got the m1 plus m2 is equal to 6.44 times 10 to the 23rd kilograms. So since the mass of Mars is much greater than the mass of Phobos, m1 plus m2 is basically the mass, or nearly equal to the mass of Mars. So then we look at the code, same thing. We have the defining objects of O2 and O1, and we added a momentum. We accounted for momentum so that the drawing doesn't drift off the screen. So this means that momentum doesn't affect anything. So, and then we have also the calculations and all that to get the answers. So our code solution was 6.44 times 10 to the 23rd, which was basically the same thing. And then we have uh, a simulation to run here to see how it works in the code. So as you can see, the small dot would be Phobos, the big one would be Mars, and the green dot in the middle is showing the center of mass. And as you can see, it doesn't move at all, showing that the center of mass is constant. So let me just get back in here. So next, we have our third problem, which is given the initial x, y, vx, and vy, and t, predict the positions and velocities of n objects at final t. So our solution was we used the force of two objects, well, given any amount of objects, the force of two objects would equal g m of one object, m of the other object over r squared, and then r would be root x x of one object minus x of the other squared plus the y of one object minus y of the other squared. So for the system of n particles, we would have to take the sum of all of these objects, and for the body of mass m, we would do F equals mv t plus 1, which would be the next object, minus the original v over the change of time. And we would solve for v of t plus 1 to get the final velocity that we want. And then for the final distance, we would just do the original distance plus the velocity times the change in time. So this force body diagram is a scenario with 4 planets, which, as you can see, each one would have to act on all the other ones, and you would have to account for that in your calculations. So the code is same thing as before. You have the objects defined and the variables that are used, and then you have a loop for the program so that you can keep adding different ones, and then you calculate the velocity, saving the position of each circle, and you making sure the positions are updated and adding the changing in time for each one, and then you have the objects obviously being drawn for the simulation. So our this is just continued on for the code, and our code solution is let me show you right here. This would be 4 different objects. So as you can see, the center of mass is still the same. It doesn't move, which goes to show. And right there, it looked weird, but one of the objects actually collided with the bigger object and combined. So you can see the center of mass is still stable. So let's go back in here. So after the first collision, a stable 3-body orbit appears to form and continues for a while, and no change is found even when running the program for many minutes. So the orbit of the 3 objects by the center of mass is stable. So for our final problem, given the initial x, y, and z, vx, vy, vz, and time, predict the positions and velocities of the n objects at final t. So our theoretical solution, it was the same thing except you're accounting for the z positions too now. So in your radius, you have to account for that by adding a z of the first object minus z of the second object squared. And most of the calculations are still the same though, from the other n body problem. So for the code, it's basically the same as the last one too, as I said, except you're accounting for the z. So we have the code solution here to show what's going on. So this is 4 different objects, and the colors work as the color gets darker blue, it goes further back. So blue is going into the page and white is coming out. So as you can see, it's as before, the center of mass is still stable, as you saw in the last simulation. So the stable orbit forms after true collision happens. However, stable orbit has a long period and is highly elliptical. So the final velocities and positions of the masses are changing as they are in a stable orbit. So for our conclusion, in this lab we explored the inner workings of the universe and the complicated ways our planet moves in comparison to other planets. We gained a better understanding of the celestial bodies and the way they interact with their neighboring bodies based on gravity and stuff like that. So some ways that this lab is applied in real world is fields like rocket science, or fields where the movements of celestial bodies and gravitational impact is imperative to understand, because without these crucial calculations, many space exploration missions would end in disaster. So the physics of celestial bodies is immensely important and will be essential for years to come, whether it be space missions or just wanting to figure out the universe, or anything that has to do with uh, the world. So thank you so much, and it's been a great year, and hope the best for everyone. Goodbye.